Today's lesson is over section 4.2, where we're talking about maximum and minimum values. So first, let C be a number in the domain D of a function f. That means that there's two values, an absolute maximum and absolute minimum, that are the overall maxes and mins for that function for that domain. Also, if we let a number f of c be in the domain of f of x, you can also find a local maxes and local mins. So that means that they're not the overall maxes and mins like the absolute max and the absolute minimum, but they are a maximum in the area, or they're the minimum in an area of the function for that part. So it's kind of like there's a little dip. Notice that also if it's a closed interval for the domain, the interval endpoints cannot be absolute maxes and absolute mins for the function. So here's some examples of what these kind of look like. So for one, I have a local min. Notice that it's not the smallest overall, but it is a dip in that point. Your local max can be an absolute max. Those are kind of the same thing. But for like 2, at the very right, you have an absolute minimum. Notice that it's also not a local min, okay? Because it's at an endpoint. 3, I can have local mins, local max. And so you can have a lot of different combinations with these. Also, if it's like at a point, so it's not differentiable at those, you can still have an absolute max and an absolute min. For 5 here, even if you have discontinuity, so there's like a obvious break, you can still have absolute maxes, local max. For 6, though, you can also have nothing because it's an open interval and there's no actual local, like no dips to give you a local min or a max. 7 shows you that you can actually have absolute maxes and mins be exactly the same value, and that's fine too. So the extreme value theorem says that if f is continuous on a closed interval, there must be an absolute minimum somewhere and there must be an absolute maximum somewhere. Okay. Fermat's theorem says that if f has a local extrema at some value of c and the derivative exists, then that means that the derivative is equal to 0 there. And that's what we kind of call a critical number. So critical numbers happen when your derivative is equal to 0 at that point, or like there's some discontinuity, so maybe there's an asymptote. Those are critical values that you want to be able to know where they're at for the derivative. If I need to be able to find an absolute extrema, this is called the closed interval method. So if your function is continuous from A to B, we want to first find all our critical numbers. So that really means I'm going to take the derivative of my function and then set it equal to 0 and solve for those values. Once I do that, then I'm going to take the values that I found, plug them into the original function, find out what their y values, that's step 2. Then I'll also plug in the endpoint values as well and find out what those y values are, and then I'll decide what are my absolute maxes and my absolute mins based on which ones are the biggest and which ones are the smallest. Okay. So for an example 1, we want to be able to sketch a function on a closed interval 1 to 5 given the certain properties. So if I'm given that it's an absolute minimum at 2, absolute max at 3, and a local min at 4, I'm just graphing where I think that could be, and there's lots of different possibilities for answers here. So for my absolute min at 2, I'm just going to make it the lowest. The 3, it's going to be the highest. 4 is a local minimum, so it's going to be lower than most of them, but not lower than the absolute minimum. And then I'm able to sketch my graph. Okay. Example 2 here, I'm looking for my absolute extrema. So first things first, I take the derivative of my function. That gets me -4 sine of x. I'm going to set it equal to 0 and solve. So sine of x equals 0, that's when sine would be 0 when I have 0 pi and 2 pi. And so notice that 0 and 2 pi are part of the endpoints of that closed interval that's given to us. So we're kind of able to do both things at the same time. So now I go back to the original function and plug those values in to figure out what those y values will be. So for f of 0, I get 6. F of pi, I get -2. And for f of 2 pi, I will also get 6. So because you get two values that are exactly the same, that means that you have two absolute maximums at that point, because since they're both the biggest. So I would say absolute maximums at 0, 6 and 2 pi over 6, or comma 6. And then an absolute minimum at my other value, which is pi, -2. And then that would be my answer. Okay. Another example of this. So first I want to take the derivative again. That gives me 2 minus 3 times 2/3 times x to the -1/3 power. That 3 and the 2/3 reduce a little bit, so I'm given that. I kind of want to be able to rewrite this so I can solve later. So I'm going to move that down. But notice that x to the 1/3, since it's a fraction, it's undefined at 0. So that's kind of like one of those discontinuity things. And so that is also a critical number that we have to keep in mind. So we'll keep that for later. But now I'm just solving, so I subtract 2 to both sides, I divide by -2, and then I cube both sides so that I can get x equals 1. So now I have all the numbers that I need. So -1, which is endpoint, 0 and 1, which are the ones that I found, and 3 is the other endpoint. And then I really just plug it back into the original function. And then I find my values. So for -1, I get -5. For 0, I'll get 0. For 1, I'll get -1. And for 3, I get -0.24. And so -5 is the smallest, or overall smallest, so that's my absolute minimum at -1, -5. And then my maximum is at 0, 0, because that's the biggest number, or biggest y value. So those would be my answers. Okay, have fun.